Okay, there's just a few things to go through before we start with the lecture. First thing, we are almost getting to class test 1, so please do not let it sneak up on you. Okay, so we've got this week, we've done the quiz. Okay, so next week we've got one more quiz, quiz 5. Okay, and then the week after that is the class test. Okay, so one more quiz, which will be on this differential calculus, and then that will be it for your revision stuff for the class test. Okay, so the class test will be all of the quiz stuff, everything we've covered up to this stuff here for this week. Okay, that's the first thing. The second thing, the class marks so far, they're looking quite good. I'm quite happy with that. Our top 2 students, if they don't want to be shy, do you want to be shy or not? Okay, you can be shy. The person coming first has got 97%, so well done to them. Very good. Yeah, clap. Yeah, so very good. 97% for the first place. Second place at 90, so quite good. Yeah, well done. Okay. And then after that, there's about 10 to 15 students on around 80%. So that's so it's the top 2, and then another 10, 15 on 80. There's a few more, 70, 75, and so on. And then around 60, it starts dropping off a bit. But so far, quite happy with the marks. Should be good. Please remember, before getting to that class test 1 and class test 2, your mark needs to be at least 50. Okay, because when you get to the class test and you see, oh, this is so difficult, your marks are going to go down even more. Okay, because the class tests are counting 12.5%. That's a large chunk for one assessment. Unlike the quizzes, which are, we have 10 of them for the semester being averaged, class tests, there's only 2. There's not much to work with there. So please, for the class test, class mark 50% before you show up for class test 1 and 2, you should be fine. For the June test, so that's at the end of the semester, your class mark should be around 60. Yeah. So if the June test doesn't go so well, you still have a passing mark of 50 at the end of it. Okay. So again, class test 1 and 2, 50% class mark, you should be fine. June test, 60% class mark, and you should be fine. Yeah. And then getting closer to the end of the year, 60% class mark before you get to the exam. That's the best, because if you have 60% class mark, you need a 40% exam mark, and then you pass the year. Okay. But if you have a 40% class mark, now you need a 60% exam mark. Going from 40% class mark to 60% in the exam, it's a little bit more difficult. Okay. Everyone clear on that? Okay, so please, class test 1 coming up, get your quiz marks up as much as possible so you have that 50. If you are around 60% so far, you're doing fine. You don't need to stress. Okay, the others on 80, please try stay on 80. Okay, if I can have 10 students on 80, that's wonderful. Okay, and then those on 90, I don't know if you'll stay on 90, but you can try. And then just a little recap on what we've done so far. So everything up to functions and limits from last week, all of that is the prerequisite stuff for university work. This week we start with university work proper. Okay, differential calculus. So everything else, that's prerequisites. Now we're going to start on the main topic for this year, and that is differential calculus. We will do that for the remainder of this term and next term. Then we will get into the next larger section, which is applications. That will be the remainder of this year, and the majority of your final exam will be on applications on differential calculus. Right? Because you're doing engineering, it will be more applications based. Okay. Then towards the end of the year, like right in the last few weeks, we will then start on integral calculus. Okay, so that will be end of term 3, term 4 will be integral calculus. And then next year, when we continue on MATH161, we will finish integral calculus and then start on the applications. Yeah. So that will be the split. And the same thing for the MATH161 exam, majority applications with some integral calculus thrown in. Okay. Is everyone clear on that? Okay. So this term, next term, differential calculus, and then the majority of the year from that on will be applications. Okay. There are a lot of applications to get through. You can see the scope on the Learn page. It will be quite a bit of work. Okay. Okay, so let's get started with the differential calculus. Now, you would have seen some of this in high school, but as I've been saying for all of the other sections, forget all of that. Okay, we're going to start from the beginning. So whatever stuff you remember from high school on derivatives and differential calculus, delete that. We're going to start from the very beginning. Okay, so let's say we have this curve f in white over here, and we have 2 points x and x plus h. So we start at x, we move to the right a little bit by h, we have x plus h, and that gives us 2 points on the curve. The line in blue going between those 2 points is called the secant line. Okay, so this blue curve here, this is the secant line. The gradient of the secant line is your normal average gradient between those 2 points. Okay, so secant line is between 2 points. The idea for the derivative that we're going to be looking at is what happens when we move that h closer to 0. So when h gets closer to 0, x plus h gets closer to x, and the secant line gets closer to this new line in pink, which we call the tangent line. So between 2 points is the secant line. At a single point, that is the tangent line. So in pink here, that is the tangent line. Okay. And as I said, for the secant line, that is the average gradient between those 2 points. The gradient of the tangent line is the gradient at that point, which we call the derivative. Okay, so the gradient of the tangent line at x, right, because this is happening at a point x, is the derivative okay, that's our new word for today, the derivative, and we call it f prime of x. Now, there's a few more notations that we'll be using. So we have f prime, we have df by dx, we have df, and so on. We'll get to that later. For now, we just have this notation, f prime. Okay, that is the derivative. So how do we define it? Well, we define it in the way that I said before. So we have this point x plus h, and we want to move it closer to x. So we want h to go to 0. Now, whenever you have that phrasing, h going to 0, you think to yourself, limits, right? So here we define this f prime as the limit of the secant gradient. So the normal gradient, or the average gradient between 2 points, we take the limit as those points get closer together. That gives us the derivative. So we want the limit, h goes to 0, of that secant gradient, which will be y2 minus y1 over x2 minus x1. So f of x plus h minus f of x over x plus h minus x. Right, y2 minus y1 over x2 minus x1. The bottom we can simplify. So this will be f prime of x is the limit, h goes to 0, f of x plus h minus f of x all over h. Yeah, you would have seen that before, right? Please put a very big box around this with a big exclamation. So everything that we're going to do today and tomorrow is based on this equation. Okay, so when we find the derivative rules, we use this equation. When we find the derivative of polynomials and trig functions and exponentials, we use this equation. everything from now on is based on this equation. Okay. So please put a big box around that. We're going to be using that quite a lot for today and tomorrow. Now, there's a few things to notice. We've got the limit h as h goes to 0. Whenever you see the limit, what do you think of? If I write down limit h goes to 0, immediately you need to think of something. What's that? Left limit, right limit, exactly. Okay, so limit h goes to 0. I'm not going to write it. You need to know it already. You need to check left limit, right limit. If they match up, then the limits exist. If the limit exists for that quotient there, so you take the limit, if it exists, we say that f is differentiable at that x value. Okay, so definition. A function f is called differentiable. Okay, there's going to be a lot of words coming up today. So please do not mix up derivative and differentiable. Okay, and differentiation. Right, they all sound similar. They're all very different. So a function f is called differentiable at x equals a at some point. Like it's continuous at x equals a. It can be differentiable at x equals a if the limit as h goes to 0 of f of a plus h minus f at a over h exists. And we know what that means. Limit from the left equals limit from the right. Okay, so that's our new word, differentiable. Very similar to continuous at a point, right? So differentiable at the point x equals a if this limit exists. If the limit exists, it's differentiable. If the limit does not exist, it is not differentiable. Very straightforward. Now, very similar to what we did with continuity, we have continuity at a point. We also have continuity on an interval. We have the same thing here. Differentiability at a point, differentiability on an interval. A function f is called differentiable on an interval. And now this is the first difference between the two. We had continuity on a closed interval. Remember from the Thursday lecture and from the quiz, the last quiz we did, continuity on a closed interval. Differentiability is on an open interval. And we'll see this makes a very, very big difference whether we talk about a closed interval for continuity and an open interval for differentiability. Okay, so it's called differentiable on an open interval, AB, if it is differentiable at all points on the interval. Very similar to continuity. Yeah. Now, over here, we have specified an open interval for differentiability. For the previous one on continuity, it was a closed interval. Now, the first person that can tell me why this is an open interval based on the definition, that's all you have based on the definition, why it needs to be an open interval and not a closed interval, will get 100% for the next week's quiz. Straight 100%, you don't even need to show up. But I will only accept 3 people. 1. Okay. 2. Anyone else? You want to give it a go? 3. Okay. So we go in that order. If you get it, straight 100%. You were first?
I would say because those having has equal to AOB. Now, regarding it says function is there, this function which will at x equals it. So x has to equal it.
Yeah, that's part of it. I'll let you expand on it. Not what? Yeah, it does have to do with the endpoints. That's right. I'll give you some time. Think about the endpoints, and then we'll move on. You can phone a friend if you want to split the points.
Fine.
No, it's defined. Yeah, the function's defined on a closed interval, but it's differentiable on the open interval. There's a very, very specific reason. It has to do with the endpoints, like you mentioned.
So,
Yeah.
and it's 15 data. We made that, so it's that.
Think about it some more when we move on. You can also phone a friend if you want. No, we don't want the endpoints. The endpoints cause us problems. I want to know why. Why do we not include the endpoints? No, it's perfectly defined. It has to do with the limits. Remember, this limit here, that's all we have to work with. That explains why. Okay, we'll get to you after. Let me be set first. You want to try again? It's 100% straight, guaranteed. I'll put the mark in now if you don't believe me. Yeah, I'll give you one more chance, then we move on.
Can't have one layer higher load if you have 1 month.
Not quite slow. Gonna have to move on. Yep. So we have a closed interval for continuity, A to B, closed interval. For differentiability, we have it on an open interval. And the reason is because of this definition here. So why? Why is it an open interval, not a closed interval? Everything is in front of you there. You don't need to know anything else. Everything is there. Yeah, you got one chance, and then we move on. No, nothing to do with shifting. The function can be on the whole real line, doesn't matter. But the differentiability is on the open interval, not the closed interval. We do one more chance, and then we move on. It's right there. I said it at the beginning when I wrote this down. I said, remember this thing. Yeah. I'll ask him and then we'll circle back. Time's up. Yeah.
So I say, limits, so when the limits not zero, so you approach it zero, that the function approaches zero. So
There's no potholes. Yeah, we'll circle back and then we'll leave it at that. Yeah, you do something to it. Very, very close. Okay, yeah, two-sided. So why can't we have close? Because you have to give me the full answer. No part marks, yeah. Full answer or nothing. So what's the problem? Yeah. So what's the problem? The specific problem we have with the endpoints. Yeah, you're right. Two-sided. But you mentioned the endpoints. There's one problem. For the level of nerves now. Almost. Come, one more chance, then we have to move on. Yeah, you're so close. Yeah, endpoints, the two-sided limit. put it together and you got it. Ask your friends, you can split the points that you want.
Not specify.
Exactly. All done. Okay. So is U3, so you'll split the points between U3. Okay. Yeah. Endpoints only have one side. If we look at the closed interval, so let's say we have a closed interval, AB, and I'm interested in the value of the derivative at x equals a, right? So I've got a closed interval, I'm interested in the endpoint x equals a. What do? I evaluate this limit. Limit h goes to 0. What does that limit mean? It means limit from the left, limit from the right. What's the limit from the right? H goes to 0 plus. On this interval, is there a right point on the right can we use? So we have our interval. Here's A, here's B, and we're going from the right. Can we go from the right? Yes. Can we go from the left? No. There is no left. X equals A is our stopping point. You cannot take the limit from the left. Does everyone see that? Okay, that's why. Okay, well done. You'll split the points. I'll get your student numbers at the end. Okay, does everyone see that? So on a closed interval, if you're looking at the point x equals a, there is nothing before a, because we're starting from a. There's nothing before a, which means there's no left limit. We have something after a, so there is a right limit. The same thing with b. There's nothing after b, so there's no right limit. But we do have something less than b, so we have a left limit. But to have one definition, limit h goes to 0, we need left and we need right. So we cannot use the closed interval. Okay. Okay, well done to you guys. You'll get your split points for this quiz coming up. All right. Let's have a look at some examples. Okay, please think of these questions for the test and the exam, right? 20 to 30% of the exam is proofs. I can ask a question like this, right? Why is it on an open interval, not a closed interval? Provide a proof. You need to provide the same reasoning. Oh, yeah, sure. So let's say we've got our function here. So open interval means we do not include that endpoint, okay? Which means that we cannot have f prime of A, and we cannot have f prime of B. Those points are removed. So what do we have instead? Everything on the inside, which is fine. Yeah, so remember open means the open circle. So those points are actually removed. So everything within those 2 points is fine. There's no issue. Yeah, it's only if we put a solid dot, means we need to look on the left of the solid dot, but there's nothing there. But if it's an open dot, we don't even need to look at it. Okay. Okay, examples. Number 1, we have f of x is equal to x squared plus 2x plus 1. We want to find the derivative at x equals 0. Yeah, so it's just at a point, x equals 0. What is the derivative? So we want f prime at 0. This is going to be the limit as h goes to 0. And now this becomes a limit problem. Okay, once you do all of the substitution, it's just a limit problem from what we covered last week. So limit h goes to 0, f of 0 plus h minus f at 0 all over h. And then we substitute and we have ourselves a limit problem to do. So this is equal to the limit h goes to 0. f of 0 plus h, we just substitute h into the expression. And then f at 0, that will just be 1. Okay. Now here, the ones can cancel. Okay. Now here, it looks like we have a problem. So when h goes to 0, the top part is 0 and the bottom part is 0. Right? It looks like there's a problem there. But it's not a problem. We just divide by h and there's no problem. So here we can do a little bit of algebra. This is going to be limit h goes to 0. We can divide the first one by h. We get h. We can divide the second one by h. We get 2. So no problem with dividing by 0 here. Limit h goes to 0. H will go to 0, so that goes away. We're left with 2. There's our answer. Okay, so the derivative of this function at 0 is 2. Okay, so once you do the substitution, it just becomes a limit problem from last week. Okay, nothing new there. Right. Any questions for this one? All pretty easy. Okay, example number 2. This one's a little bit more challenging, not too bad. So we have f of x is equal to absolute value of x. So we want the derivative at x equals 0. And here we're going to arrive at our first problem. So let's just follow what we did before, exactly the same, and then we're going to see what the problem is at x equals 0. Yeah? Oh, sure. Yeah, so we do everything exactly the same. We set up the limit problem, take the limit, and something's going to go wrong with the limit. Okay, so let's see what that is. Now remember this function, absolute value of x, we can write it as a piecewise function, okay, like we had in the tutorial, yeah? So we can write this as just x. If x is positive, we just leave it alone. If x is negative, we need to put a minus sign to make it positive. Yeah, so it's a perfectly fine function. It looks something like this. Yeah, it's continuous. You would have shown that in the tutorial. So it's continuous. Everything's nice and fine. Let's have a look at that limit. So we want f prime at 0. So this will be the limit as h goes to 0. Absolute value of 0 plus h, like we had before, minus absolute value of h, absolute value of 0, all over h. Right, I've just substituted h there and 0. Okay, so now 0 plus h is just h, so we can leave that alone. The absolute value of 0, that just goes away. And we have an h at the bottom. Now we have an issue here. This absolute value of h behaves very different when we look at the left and the right limits. So in the previous example, limit h goes to 0 of h. If we look at it from the left and the right, it's the same value. There's no issue. Over here, there's a very big issue, whether we look at this from the left or from the right. Yeah. So we're going to have to split this up into the limit from the left and the limit from the right, and we'll see they actually don't match up. So the limit doesn't exist. And that's because of this absolute value. We need to look at the left and the right. So let's check. So limit h goes to 0 minus, we're looking at the one from the left, of absolute value of h over h. So 0 minus means it's negative. The absolute value of something, with it being negative, we need to put a minus sign in front. We get minus 1. Let's check the limit from the right. So we have the limit, h goes to 0 plus. Now h is positive. The absolute value of something positive is just whatever's inside. So we have absolute value of h over h. So that's plus h over h. This is plus 1. Now we see the problem. So this limit with the absolute value, we have to split up into left and the right. The left one is minus 1. The right one is plus 1. The limits do not match. The limit does not exist. The limit does not exist. And we go back up a tiny little bit. A function f is called differentiable at x equals a if the limit exists. What did we just show? The limit does not exist. So if it's differentiable when the limit exists, if the limit doesn't exist, it is not differentiable. So f of x equals absolute value of x is not differentiable at x equals 0. But it is differentiable everywhere else. At x equals 0, it is not differentiable at that single point. Everywhere else, it's fine. And we can see that in the following picture. We see that on the left side, the derivative was minus 1 from the left limit. On the right limit, it's plus 1. At 0, it is not differentiable. So we can sketch f prime. So remember, here was f. That was our function there. Now we're going to sketch the derivative. On the left side, it was minus 1. Open circle, we are not including x equals 0. It is not differentiable there. And then on the right side, we said that the limit was plus 1. So open circle here. This is f prime. Here. So this is the difference between differentiability at a point and on an interval, right? So here, there's a problem just at that point. Everywhere else, it's fine. The function is differentiable outside of that point, but at that point, it is not. Yeah. So we see on the left and the right, it is both open circles. Okay, so f prime is not defined. It's not defined at x equals 0. Everywhere else, no problem. Everyone okay with this example? Okay. And then just something to note before we get into more terminology. We said f over here was continuous. You showed that in the tutorial. Not the tutorial, the homework stuff for the week. So if we look at the left and the right, everything matches up nicely. There's no discontinuities. F is continuous. Okay. Absolute value of x is continuous. F prime is discontinuous. Why? Yep. Remember the list. There's 3 things. Is f defined at 0? No. So that first condition fails. Does the limit from the left and right match? No. Second condition fails. Third one, we don't even need to check. Please remember those 3 conditions for continuity. So f prime is not continuous. What type of discontinuity is it? Jump. There we go. So f prime is not continuous. In fact, it is a jump discontinuity. Okay, please remember your classification of discontinuities. Jump discontinuity, infinite discontinuity, removable discontinuity. Okay. Does this make sense? Okay. So this takes us to the idea of differentiability classes. So what this is about is classifying functions into classes. So we say, okay, well, this function you give me class 1. This function you give me class 2. based on whether or not it is differentiable and how many times we can differentiate it. Yeah, so that's the idea. You give me a function, I can say, oh, it's class 1, class 2, class 3. We want to try to group them together based on their differentiability. There's a few definitions we need to get through. So number 1, definition. A function f is called continuously differentiable. Remember, I warned you last time, a lot of definitions and terminology. So it's called continuously differentiable. So it's not continuous, it's not differentiable. This is a new thing now. So it's a third thing. Continuously differentiable if, here's the condition, f prime exists. What do I mean by f prime exists? It means we go back here, we check the limit exists, that means f prime exists. Okay, so whenever I say a new thing, you go back and check the old thing. So here f prime exists. Okay, what does that mean? You go back and then you check the definition. Okay, that limit must exist. Okay, f prime exists, and not just that it exists, and f prime must be, any guess? Look at the wording. Any guess? No. Oh, someone said it? Continuous, yeah. Sorry, no points for that one. Yeah. So a function f is continuously differentiable if f prime exists and f prime is continuous. Now, at this stage, wherever you are in your notes, the next page, leave it blank, wherever you are. Okay, next page, please leave it blank. You're going to summarize all of the definitions we have so far. So, finish up with what we've got here, but the next page, keep it blank. On that page, you're going to write down the definitions from top to bottom. So at the top, when a limit exists, you're going to write, when does a limit exist? Left limit equals right limit. You put that down as number 1. Number 2, continuity. There's those 3 things we needed to check. Number 3, differentiability. You write that limit must exist. You put that down. After that, you put continuously differentiable. You put that definition down. And then there's a couple more. You put that down on that page. And you color in that page. You put stars on that page. Whatever you need. Do not forget that page. Okay. So we're going to finish up with this. The very next page, leave it blank. And for homework, please put all the definitions from top to bottom that we covered. Okay. Limits, continuity, differentiability, continuously differentiable, and the next few to space it out nicely. We will see that again many more times, so it's nice to have it in one place. Okay. Next, definition. There's quite a few coming up. So definition. The set of all continuous functions. Okay, now we're mixing sets and functions and continuity. Right? Okay, so the set of all continuous functions is given by a capital C and a superscript 0. Okay, so it's not an O at the top. It's a capital C and a superscript 0 at the top. Now, sometimes you'll see it just as this. Other times you'll see it as this with some domain. Okay, but we're not going to put in the domain. If I give you a function, you know how to calculate the domain. So I'm not going to put that. Okay, so that is the set of all continuous functions. We know how to check continuity. Okay, if I give you a function and I say, does it belong to the set? You can check. Definition. The set of all continuously differentiable functions. So that's from from what we had over there, continuously differentiable functions. Okay, is given by something very similar. It's a capital C and a superscript 1. So what this means, what the 1 means over here, is you can take one derivative of the function and the result is continuous. So we go back to the definition. We take one derivative, that's what the 1 means, so it's f prime. F prime is continuous, we call it continuously differentiable. Okay, we can extend this to higher order derivatives. Okay, and we get the set CK. What the K means is we can do K derivatives and the result is continuous. So again, C0, we do no derivatives, the function is continuous. C1, we do one derivative, the result is continuous. CK, we do K derivatives, the result is continuous. Okay. So here, that's CK, so C0, C1, CK. These are all sets, right? The sets of the functions. What we can do with these sets is form a chain of inclusions, A subset of B, in the following way. CK is a subset of the next one, and it goes down to C2 is contained in C1, which is contained in C0. So as you do more derivatives, the sets get smaller. Okay. So we start with C0. C1 is a subset of C0. C2 is a subset of C1, all the way down to CK is a subset of everything else to the right. Now, please don't be scared by this one. We write C infinity. I said don't be scared. Okay, so C infinity is the set of all smooth functions. We will see this in a couple weeks. So C infinity is the set of all smooth functions. Okay, this will be important for later on. So what do we mean by smooth? We mean that the function looks pretty smooth. So examples includes any polynomial. They look pretty smooth. We call it smooth. Trig functions, like sine and cosine, those are smooth functions. Exponential functions, those are smooth functions. Okay, so in terms of pictures, they look pretty smooth. There's no points or cusps, as I said in the last Thursday, on these functions. Okay, they look smooth, we call them smooth. So technically what it means is we can do any number of derivatives. For example, if I give you a polynomial, you can do the first derivative, second, third, fourth, fifth, any number of derivatives, and the result is again continuous. Okay, so any polynomial, any trig function, any exponential, those are all smooth. We can do as many derivatives as we like. And that's going to become important later on. Okay, so all these functions that we know from before, those are all smooth, which means we can do as many derivatives and there's no issues. No issues with domain, no issues with the range, no problem points, nothing like that. We just keep deriving. You can use that without proof. Okay. So if I say calculate the 40th derivative of sine, there's no issue. You don't need to check anything. You just do the calculation. Now there's one more thing. So this is the set of all smooth functions. There's one more to the left, and that is C omega. Don't ask what that is. You will be scared. This is a subset of smooth functions. These are the analytic functions. Okay, we will see these later when we do Taylor's theorem. Okay, a couple weeks from now. Okay, so I'm just giving you the terminology for now. Later on, we will be using these. Okay, so when we get to Taylor's theorem in a couple of weeks, we will be working with analytic functions. Okay. Taylor's theorem doesn't work with the other ones. It must be analytic. Okay, so that's quite a lot of terminology. Like I said, on the next page, please leave it blank and fill in all of those definitions. Now we're going to do a quick proof before we get to some more derivatives. So notice this chain of inclusions here. We are going to prove this very last bit. Okay. We're not going to prove anything else in the chain, just that last bit. So a test and exams, I'll only test you on that last subset. So what we want to prove is that the set of differentiable functions is a subset of the set of continuous functions. Let's have a look at the proof. Okay, so we want to prove C1 is a subset of C0. So what does this mean? If I have a function f from the first set, I know it belongs to the second set. This goes right back to when we did set theory with subsets. So if a function f belongs to the first set, then f belongs to the second set. That is what we mean by subset. If you forgot your set theory, please go back and revise that. Okay. So, proof. Let's start off with what is given, and we want to have what we want to show, and then we'll put the proof together. Okay, so let's start. Need to show what? If f is differentiable, then it is continuous. F is differentiable, then f is continuous. Okay. Now we want to set up our proof, so let's write down what's given. What's given? Well, we know that f is differentiable. What is the definition for differentiability? That limit of the quotient must exist. Right? That's given to us. We know it's differentiable, so we know this limits exist. That's the definition for differentiable at x. So what do we want to show? We want to show that f is continuous. What's the definition for f being continuous? Let's make a little note on the side here. It means that the limit x goes to a, f of x equals f of a. Remember that? We wrote it down, we put a big box around it. That's the definition for continuity. Everyone clear on those two? Yeah. So let's set up our proof. So what I'm going to do is start with this side over here. That's what we're trying to show. I'm going to have f of x, and this f of a I'm going to take over to the left side. So we're going to start with f of x minus f of a. Okay. So I'll just take the f of a over. I'm going to rewrite it a little bit as f of x minus f of a over x minus a times x minus a. Okay, the x minus a cancels and the left side equals the right side, no issue. Next, I'm going to take the limit as x goes to a on both sides. Okay, so we have f of x minus f of a over x minus a times x minus a. Okay. Now we're going to do a little bit of limit work. We know our limit laws. Let's use them. On the left side, we have the limit x goes to a of f of x minus f of a. F at a is a constant. The limit of a constant is just the constant back, right? It's unaffected by the limit. So this is going to be the limit x goes to a of f of x minus f at a. I'm not going to write down which limit law it is. You can look that up. Okay, so it's a constant. The limit of a constant is the constant back. Next limit law. I've got a limit of a product. I can write it as the product of the limits. So that's one limit. And I'm going to have the limit of the second one as well. Okay, so I've just been using my limit laws, nothing else. Okay, that first bracket there, what is that going to be? We have f of x minus f of a over x minus a. What is that? If I took the limits away, what is that? Oh, you said? What is it? Yeah, f of x minus f of a, y2 minus y1 over x2 minus x1. What is that? The gradient. What's the limit of the gradient? It was the very first thing we wrote down. Look back in your notes. Very first thing. It's the derivative. It's the limit of the gradient, right? The tangent line. So that's the derivative. So we have the limit. X goes to a. F of x minus f of a equals f prime at a. Now, why is it safe to write that down? This limit. I don't know what f is, but I wrote this as f prime. Why is it safe to do that? Does the limit exist? Of course it exists. It's given that it's differentiable. So it is safe to write the gradient down, f prime at a. Okay, next. This limit on the right there, what is that? Limit x goes to a of x. It's one of the limit laws. Check your books, flip back a couple pages, go to your limit laws. We set up that table with 8 of the limit laws. This was the last one, I think. Okay, those not flipping back, I assume you never did the work. Yep, you got it? Very last one. Yeah. Yeah, for what constant? Limit x goes to a of x. That's just a, yeah. It's not a trick question, just a. Okay, a minus a? Yeah. No, it's nice. A minus a? 0. Okay, so we have the limits. X goes to a f of x minus f at a is equal to 0. This minus f of a, let's take it over to the other side. This looks familiar. What does this mean in the box? F is continuous. So what did we start with? We started with f being differentiable. So we started with it being differentiable. We did a bunch of proof stuff, and we ended with f being continuous. So what does that mean? If it is differentiable, then it is continuous. And we're done. Okay. Now something very, very important. The subset relation, right? If it is differentiable, then it is continuous, only works in this direction. You cannot swap the ordering. Yeah? Zero. What is the limit as x goes to a of x? Limit law number 8. Read it to me. What's limit law number 8? X equals a. So I have a minus a. What's that? 0. Yeah. Yeah. So if f is differentiable, then f is continuous. You cannot write this the other way around. So I'm going to write this down and then put a big cross through it before you memorize it. If f is continuous, then f is differentiable. And before you have a chance to memorize it, I'll put a big line through it. Okay. It does not work the other way around. If f is differentiable, then f is continuous. That is fine. F being continuous, then f being differentiable, not fine. And we see that in the in the second example we did over here. F of x equals absolute value of x. Is this continuous at x equals 0? Yes. Is the derivative continuous? No. No. It is not differentiable at x equals 0. So going this way works, going the other way, it does not work in general. Sometimes it does, sometimes it doesn't. In general, we cannot go in the reverse direction. So please, this first line, put a big box around it. The second line, don't even write it down. It's wrong. Yeah. Any questions so far? Okay. So we've covered quite a lot of theory work. Okay. I hope everyone managed to keep up. There's a little bit more to do. Not too much. We'll get through it. But please, this last line, please put it at the bottom of that blank page. So you had all of the definitions, right? And then please put that in a big box at the end there. That's our final result for the section. Okay. Any questions before we move on to the rules? Oh, good. Okay. The rules for derivatives. Okay. There won't be any more proofs after this. A few calculations, but no proofs. Okay. So the proof that we had before, that's the only thing that you need to worry about. So if it is differentiable, then it is continuous. So you need to know the proof, you need to know how to prove it, and you need to know that end result. Okay. That's it. The rest is just definitions, and going on from now on is just calculations. Okay. So the rules for derivatives. So number 1, if I have the sum or difference of two functions and I take the derivative, this is the same thing as the derivative of the first one plus or minus the derivative of the second one. Now, you can prove this using the definition. We won't be doing that. Okay. So if you go right back to here, this definition, you can prove all of these rules using this definition. Okay, we won't be covering that. Okay, I will save you from that. Okay, so you do need to know the rules. You do not need to know how to prove them. Number 2, if I have some constant times the function and I take the derivative, then the constant can come out. So it will be c times f prime. Together, rule number 1 and rule number 2 defines a property called linearity. Okay, please put a big box and an exclamation mark next to that. So if I tell you something is linear, what I mean is that if I have f plus g, I can separate it into f prime and g prime. I can split it like that. If I have any constants inside, I can take the constant outside. If those two are satisfied, those two properties, we say that it is linear. Nothing to do with the straight line linearity, forget that. It is a property of the derivative. Okay, so the derivative is linear. Later on, when we do integral calculus, the integral will also be linear. Okay, so it's a property that these things can have. Number 3, if I have a product and I take the derivative, I can write this as f prime times g plus f times g prime. Since it's a product, we call it the product rule. Number 4, if I have a quotient of f over g and I take the derivative, then this is equal to something pretty messy. To be honest, I have to look up this formula every single time. You need to memorize it though. This is going to be f prime g minus g prime f over g squared. Okay. F prime g minus g prime f over g squared. Say it to yourself 10 times, you'll probably get it. This is a quotient of two things. We call it the quotient rule. Okay. And number 5, if I have a composition f of g prime, we know how to do compositions, all of that stuff from before. This is now given by f prime of g times, and then the derivative of the inside function. Okay, so this is a composition, so we call it the chain rule. Okay, I did not name these, so there you go. If it's a product, it's a product rule. If it's a quotient, it's the quotient rule. If it's a composition, somehow it's the chain rule. Okay, you just need to learn those names. So please learn these names for the different rules, because as we go through the calculations, I'll say we are using the product rule. You need to be able to go back and see, oh, that's the product rule. Or if I say we have to use the quotient rule, you have to go back and see what that is. Okay, so please learn the names for those. Okay, and then please over here, rules for derivatives, put a big... These need to be memorized. They will not be given to you. Yeah. Sorry? If the? We take g to the top. No, this is f over g. Yeah, no, it's a fraction. So f at the top, g at the bottom. It must be written like that. If you take g to the top, you're doing some funny things there. Yeah, no, please, fraction like this. We'll do examples so you can see how it's set up, but don't start moving functions around. It makes it more complicated. Okay. Any other questions before we move on? All good. Okay, like I said, please put lots of exclamation marks. These need to be memorized. They will not be provided to you. Okay, there's no formula sheet for this. Okay, next. Derivatives of important functions. So we go back to the list of those important functions I wrote out earlier. I hope you all have that list, right? The elementary function list. Okay, so from that list, we're going to do the derivative of each type of those functions. So for today, we're going to do the long calculation on how we get the derivative. That is only for today. After that, you just learn how it's done. You do not show all of the working. Okay. So, number one, polynomials. Okay, so I'll show you the long way once. Once we've done that, you do not do it the long way again. Okay, please listen to the question very carefully. So if it says, use the rules for derivatives, please do not do it this whole long way. You're wasting your time. Okay, polynomials. So we know that a standard polynomial can be written in the following way. Let's say it's 3x squared plus 2x minus 1, for example. We would like to take the derivative of this, as we say, from first principles, right? Using the long way. Now, we know from the rules for derivatives that the derivative can be separated on each term and constants can come out. Okay. So here, if I want the derivative, so now I'm going to use this notation, d by dx. This means the same thing as f prime is equal to d by dx of 3x squared plus 2x minus 1. I can separate it into the individual terms and the constants can come out. So I'm going to do that. So this will be 3 times d by dx of x squared plus 2 d by dx of x minus d by dx of 1. I can separate it out like that. So what we're going to do for the long way is calculate the derivative from first principles, the long way, for one of these terms. Okay. So we'll do first principles derivative Right. You know what first principles means, from the definition. First principles derivative of x to the n. So if we do it the long way just once for x to the n, then we can do it for x squared, we can do it for x, we can do it for any power like that. Yeah. So let's go ahead and do that. So we've got our function f of x is x to the n, and we don't know what n is, it's some power. It can be x squared like the first term, it can be x to the 1 like the second term there, some power. So f prime is going to be the limit, h goes to 0, f of x plus h minus f of x all over h. Right, that's first principles. We go right back to that first definition. Okay, so let's substitute, expand, and we'll get our answer. So this is going to be the limit as h goes to 0, x plus h to the n minus x to the n all over h. Okay. And now again, we don't know what n is. It's some exponent. Could be 2, 3, 4, whatever. What we're going to do now is expand out that binomial using the binomial theorem. So this is going to be written as the limit, h goes to 0. The sum, k goes from 0 to n choose k of x to the n minus k. There's no laughing. You know what the binomial theorem is? Oh, you didn't do the tutorial work. Oh, no. Okay. So please, you go open your textbook. You go to the ending bit over here. And then you look for the binomial theorem that you should have done in week 1. Let's see over here. It's ellipses, all the stuff you should have covered. In week 1, I said, please go over the algebra. Somewhere here, there's trig stuff to go through, Right, I said if you don't know your trig stuff, you go to the textbook, you look at your trig things, all the way here, trig functions, all this. There, binomial, sigma notation, all the stuff here. There we go, limits, all that thing there. You don't remember that? Yeah? No, not the written one, that was on the exponents, the one from the textbook. You didn't do the textbook one? No, that's only half of it. The textbook's the other half. So did you just do the other one? No. Textbook, please. All of the tutorials, there's the stuff that's written in that PDF, and there's the little section over here. What's it? Please, you have to go over that. I assumed you did already. This bit. This one, tutorial exercises, A, B, D, E, G. From here. This one, exercise A. You did that one? You did that one. And the others? You left the others out. No, please. No, this one was just the numbers, inequalities, and stuff from the high school. If you didn't know the other stuff, you must go over it. Okay, this isn't baby school. I'm not going to tell you, oh, you don't know this, you must go over this. You don't know this, you must go over this. You need to know what you don't know and go over it. Okay, please. So this stuff here, under the appendix, where's the sigma notation here? Where does it start? A34. Please write it down. A34 onwards. Please go over that. Okay, if there's gaps in your knowledge, you need to fix it before we get to the stuff. Okay, factoring, binomials, factorization of quadratics and cubics, FOIL, dots, all of that stuff. You have to know it. Trig functions, sum rule, double angle, half angle, everything comes up. You have to know everything. Yeah. Please, if you don't know your trig identities, go over it. You don't know your sigma notation, go over it. Everything you have to know. Okay, so please go over that. So we have the sum. N choose k, x to the n minus k, h to the k minus x to the n over h. Okay. I'm sure you guys have done this. You have a plus b cubed. Did you cover that in high school? A plus b squared, you know? A squared plus 2ab plus b squared. A plus b cubed, you did that. A plus b to the 4. Yeah, that's the binomial. Okay, if you don't know it, please go through it. Okay, so we're going to write out the first few terms of the sum. We'll see there's some cancellation, and then we'll get our answer. So this is going to be equal to the limit as h goes to 0. We'll write out the first few terms. So the first term will be x to the n plus n choose 1. Right, n choose 0. What's that? You definitely did the choose function in the probability and counting. So math paper 2, counting. What did you do? You know, you got a license plate with 4 numbers and 4 things and you swap them around. You really didn't do it. Yeah, counting principle with the choose function. You didn't. Hey, okay. Homework, choose function, binomial, please. Please go over that. What did you do all year? Counting, arithmetic, 1 plus 1. Hey, come, please, homework, binomial and the choose function. Please go through that. I can't do that now. We're already wasting too much time. Okay, so we have n choose 1. X to the n minus 1 times h plus dot. There's some other terms. We don't have to worry about those too much. minus x to the n all over h. Okay, please go. If you don't understand what I'm writing there, as soon as this lecture finishes, you Google that and you learn it. If you don't know it for tomorrow, you're going to be behind. Okay, you're already behind. You're going to be more behind. Okay, please, binomial theorem, choose function. Hey, you have to know this. It's expected from high school. If you didn't do it in high school, I'm sorry, I didn't teach you, but you do need to know it. Okay. So here we have x to the n minus x to the n. They cancel. And we're left with all the terms in the middle. But we see that second term has an h. It cancels with the h at the bottom. N choose 1 is n. If you don't know what that means, please Google it afterwards. You need to know this. This is going to be the limit. H goes to 0 of n, x to the n minus 1. The h's cancel. H at the top, h at the bottom, that goes away. Plus, all of the other terms where I put that dot, 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 will have some h. It will be h, h squared, h cubed, and so on. So we can factor out an h, dot, 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 like that. Okay. So like I said, after this, you Google it, you fill in your details from your missing knowledge. Okay, so we end up at that. When h goes to 0, the first term is unaffected. There's no h's. The second term and all the terms afterwards all have h. So they go to 0. So here, this is equal to n, x to the n minus 1. Okay. Now we do this whole long calculation, and we don't do it again. Okay, we know the answer now for x to the n. The derivative of x to the n is n x to the n minus 1. We write that down as a rule. We do not do it the long way again. If I ask you to do it the long way in a test, you will need to know how to do it. But if it's just a calculation, as we'll see here for this example, we just use the rule. So we have a new rule, the power rule. D by dx of x to the n is n x to the n minus 1. Okay. Now, for the binomial theorem, this n was a positive integer, right? A plus b squared or a plus b cubed or something like that. We can extend this to real powers, but then it's a bit more complicated to prove it, so we're not going to do that. So here, this was n element of natural numbers. We can extend it to real numbers, but we won't do the proof. Okay. So that will be d by dx of x to the p is p x to the p minus 1, where p is some real number, not 0. Okay. So we proved the first case. The second case we're not going to do. If you don't know the binomial theorem, the infinite one is just wasting time. Okay, please go through that binomial theorem. Okay, you have to know it. Okay, so we have the power rule. So I'm not going to ask if you have any questions about that. You're going to have to just do that in your own time. But this rule over here with d by dx, x to the p, please put a big box around that. Okay, I'm slightly worried about the other stuff you don't know from high school. Okay, maybe next lecture we'll have to see what you really know and what you don't know. Okay, because when we get into the applications, just as an example, surface area of a cylinder. Do you know that? Yes. If you have a cone, surface area of a cone. Yes. Volume of a cone, volume of a sphere, surface area of a sphere. Okay, there's more yeses than no's, so that should be okay. Okay, but that's this binomial theorem is very worrying. Okay, you have to go through it. Okay, I think I've said it 5 times now. I think you understand why. Yeah. Let's go through the next few. Okay, so a quick example before we go on. Okay, quiet please. So d by dx of what we had here, 3x squared plus 2x minus 1. Okay. So we're going to go through it step by step like we did before, and we're going to use this new rule that we derived, the power rule. So we know that the derivative is linear, so constants can come out, and we can separate the terms. So this will be 3 d by dx x squared plus 2 d by dx of x minus d by dx of 1. And we'll go through it term by term. So we're going to have 3 and then d by dx of x squared. So in that case, n is 2. So what do we do? The derivative is n times x to the n minus 1. So the 2 comes down as an n, and then we subtract 1 from the exponent. So the new exponent is 1. Yeah, the derivative of x will be 1. Because we take 1 from the exponent, so the exponent is 0, ends up being 1. The derivative of a constant, 0. Okay, so this will be 6x plus 2. Okay, so please don't do it this whole long way here with this whole proof. Okay, if I say use the rules for derivatives, you just use the rules. Okay, you don't do it that whole long way, unless it says from first principles or derive the rule or something like that. Yeah?
The polynomial question you got before we did the polynomial. That 100.
That's first principles. That's using the definition. This is using the rule derived from the definition.
Didn't even get asked to
Yeah, so it will say specifically from first principles. Then you go back here and you look at the definition. This is from first principles. It means from the definition. Otherwise, if it says using the rules, then you use these rules that we wrote down here, and you use the rules that we're deriving now. Yeah.
So that's where this equals that you have to use that choose on to.
Yeah. Back to the definition where you substitute the function, take the limits, all of that stuff. Yes?
Probably not. Is it necessary to do the two sets of steps, or you go straight into the answer?
Straight to the answer if you want. However, if you go straight to the answer and you're wrong, you get 0. If you show the steps, you can get your part marks. Because if you go straight to the answer and you don't show you're working, what am I supposed to put ticks on? You got nothing. Okay. Yeah, so if you're confident and you want to just jump straight to 6x plus 2, you get all your marks. If you jump straight to 6x plus 1, you now get 0. Yeah, I mean, what am I supposed to do? You wrote down just one line of a wrong answer. Am I supposed to give you part marks for thinking? No. Yeah. Any questions on this one before we move on? All good. Okay, so polynomials, we can deal with that now. You can use the power rule. Next, trig functions. Okay, so that's number 1, polynomials. Number 2, trig functions. Okay, from first principles, as we did before with the polynomials. Okay, like I said before, we do it once the long way, we write down the rule, and then from then on you use the rule. Unless the question says from first principles. Okay, so first one, we want the derivative of sine x. Yeah, again from first principles. So what is this going to be? So this is going to be the limit as h goes to 0, sine of x plus h minus sine of x over h. Right, first principles, that's the definition we started the lecture with. Now, I did ask you about your sum and difference angle formulae. I didn't hear too many no's, so we're going to use that. If you don't know it for sine and cos, you better write it down afterwards. Yeah, you have to know how to do the first principles derivative for sine, cos, tan, all of those. and inside you have x plus h, you need to know your sine a plus b formula. None of that is given to you. All of that you have to know. Okay, so that will be the limit. H goes to 0. Please tell me what that is. Sine x. Cos h, yeah. Sine h, yeah. Cos x. Okay. A few people that said it, I'm happy. The other ones, maybe you know it. I don't know. Okay, minus sine x all over h. Now, once we do the substitution, this becomes a limit problem, right, from what we did last week. Yeah, so the derivative stuff, that's just the substitution. Now it's a limit problem. What we're going to do is collect the sine terms. We have sine x in the front, sine x at the end. We're going to put that as one term, and then everything else we're going to put to the side. So this is equal to the limit, h goes to 0, sine x, what's left over? Cos h minus 1 over h. Right? Everyone see that? Okay. Plus, what's next? We have the middle term, the cos x sine h term. So plus the limit, h goes to 0, cos x sine h over h. Now, sine x and cos x, that has nothing to do with h. We can take it outside of the limit. Yeah, that's second limit there. What is that? 1. Yeah. We did that last week. Okay, so you see how everything builds up on everything else, right? We did that limit sine x over x when x goes to 0. We did that last week, a whole long proof. We showed that it was 1. Now here, in the first principles derivative of sine x, you see that limit appears. You need to know that that is 1 from what we did last week. If you forgot it from last week, now you can't do this one. Okay, so please, every week builds up on top of each other. You cannot learn last week and now forget for this week. Okay, it all comes up again. Okay, so that's 1. Now we need to do this other limit here. It's slightly longer, so we'll do it on the side here. So we have the limit. H goes to 0. Cos h minus 1 over h. Quick check. If we substitute 0, what does the top become? Cos of 0 is 1. 1 minus 1. Okay, top is 0. That's fine. The bottom, 0. That's not fine. Can't be dividing by 0 like that. So we're going to have to do something else to evaluate this limit. Now, there's a trick to evaluate these limits with trig functions, and that is by multiplying by whatever we have there, cos h. Instead of the minus 1, we're going to put a plus 1. Why do we do that? Because we want something like a minus b and a plus b, right? Your dots from high school. Difference of 2 squares. Okay, so let's expand out the top. We leave the bottom alone, and hopefully we can simplify this limit. So this is going to be the limit as h goes to 0 of expanding the top, cos squared minus 1. Over h, cos h plus 1. Okay, now all the stuff we learned about limits now comes in. Okay, cos squared minus 1. We can simplify that. What's cos squared minus 1? Not sine squared? Negative sine squared. Okay, now we're going to use our limit laws. So we're going to write this as a product of two limits, okay, using our limit laws. And then that will simplify this quite a bit. So firstly, this minus can come out. Then we have the limit h goes to 0. I'm going to take one of the sine terms and divide it by h. I now have one more sine term left over and the cos term at the bottom. I'm going to put that in my second limit. Okay. Everyone see what we did? So one of the sine terms I put for the first limit, the other sine term I put for the other limit. And now we're going to evaluate this. Okay, first limit, what is that? 1. Good, from last week. Remember I said put a big box around this. We're going to see it again. We're seeing it again now. Okay, next one. If I put h 0 for the top, what do I get? Sine of 0 is 0. Okay, there might be a problem. Let's check the bottom. If I put 0 in the bottom, what do I get? 1 plus 1 is 2. There's no problem anymore. 0 at the top, 2 at the bottom, no issue. This is 0. Okay, so please, all the limit stuff we did last week, the limit laws, the sine x over x, all of those things, right? We did it last week. You still need to know it this week. Okay, so that's 0, which means this first term here is 0. And the second term, that limit was 1, we left with cos x. So after all of this, the derivative of sine x is over here, cos x. Okay, so please write this down. Put a little box around it. Okay, so the derivative of sine x is cos x. For homework, you're going to repeat all of this again to find the derivative of cos x. Okay, so from first principles, find the derivative of cos x. You should arrive at minus sine x. Okay, so please check that. So the steps are exactly the same. It's just your limits will be slightly different and your sum angle formula here will be different. Okay, but everything's the same. Similar, please go through that for homework. And homework is not a maybe thing to do. You must do it. Okay. Well, if you want to pass, you can do it. Otherwise, that's fine. I've already got 10 or so on 80%. So I got my favorites. If you don't want to play along, that's fine. Okay. So the derivative of sine, the derivative of cos. Okay, cos 1 you do for homework. Next, the derivative of tan. Okay, now for this one, for homework, you're going to do it the long way. I'm going to show you a slightly shorter way to do it, but you need to know how to do both. Okay, so again, homework, please do it the long way. Tan of x plus h minus tan of x over h. Do the limit, see what you get. A much shorter way is to write this as the derivative of sine x over cos x. Right? Because tan is sine over cos. And now, what do we have? We have the derivative of a quotient. What can we do? We have a quotient. We can do the quotient rule. Let's use the quotient rule. Okay. So when we use the quotient rule, you go back to your rules for derivatives. You go down to quotient rule. We're just filling in the pieces now. So sine is at the top, cos is at the bottom, and we know the derivative of sine, and we know the derivative for cos. So you can fill in the functions there, all divided by g squared, so it will be cos squared at the bottom. Does everyone see that? Okay, so let's fill it in. So this is going to be sine squared x plus cos squared x over cos squared x. Right, because it's f prime g, so there we get squared minus g prime f, but we get a minus sign from the cos, so it'll be a plus. Cos squared over cos squared. Sine squared plus cos squared is 1 over cos squared. Now, we're not going to write it like this. The way we're going to be using the derivative of tan is by noting that 1 over cos is 1 over cos is sec. Thank you. So cos squared will be sec squared. That's how we're going to be using it, not as 1 over cos squared. We're going to be using it as sec squared. Okay. You get the idea of how we do these derivatives now. Okay. Now, please put a big box with a lot of stars for this next thing. The derivative of trig functions. So I'm going to list out all 6 that we need. You need to memorize them, right? That's just the way things are. They won't be given to you. Derivative of trig functions. Okay, it's quite easy to memorize. Just give yourself 5 minutes or so. You'll know it already. Okay, so the ones we've done so far, the derivative of sine is derivative of sine? Cos. Yeah. Okay, so this is for the one column. Then down the other column, we're going to look at the derivative of cos. So I'm going to arrange it this way because we have sine on the one column and cosine on the other. Remember your cofunctions? Sine and cosine, tan and cotan, sec and cosec. No, don't tell me you didn't do that in high school. What? You don't know the cofunctions? Oh. Cotan. Cot. Oh my God. You're going to make me pull my hair out. Yeah. Sine, cosine. Right? Tan, cotan, cot. It's called co for a reason. This is why. So we have the derivative of cos is minus sine. Okay, quiet down, please. Next, we have the derivative of tan. We just found this now is sec squared. And then on the other side, for the cofunctions, the derivative of cot, very easy to do. The second column comes with a minus sign, so we put a minus sign. The first column had sec. The second column is the co-column, so it's cosec. So we have cosec squared. So you look at the first column, so cos. What's the co thing for that? Sine. Well, you need to put a minus in front. We have sec. The co is cosec, and you put a minus sign. And then the last two, the derivative of sec. Do you know this one? Have you seen it before? No. Okay, that's fine. So this is sec x tan x. And the derivative of cosec, you could probably guess this one. It's in the co column, so we put a minus. Cosec. And then? What's the other one? Cotan. Yeah, there you go. Easy stuff. Okay. Okay, please put a big box around this one. Okay, a lot of boxes today. Okay, now we will be doing lots and lots and lots of examples of these. Trust me, when you look at the tutorial, your Saturday and your Sunday is gone. Okay, there's plenty examples to do. Okay, so please go through that. But these ones, very important to know. Okay, otherwise when you get to the test, you're going to be trying to do it the long way, you're wasting your time. If I say the derivative of tan, you mustn't be doing this whole long way because you forgot. You must just put down sec squared. Okay, it's just like, something to memorize. Okay, last thing for today. So we've done the general first principles formula. We've done polynomials. We've done trig functions. Next is exponentials. Okay, if you're laughing about how much work this is, wait until we get to the applications. Okay, it's going to be an application per week. We're going to go through optimization, sketching, error approximation. 1 week, next thing. I think there's about 8 to go through. Okay, so please, this is not fast. Okay, if you can't keep up with this, I'm sorry, that's just the way things are. Okay, next thing, derivatives of exponentials. Right, just before I forget. So here, I don't know if you've been looking at the learn page for the syllabus. I'm going to put a little marker just to show, where you should be with the syllabus. So over here, syllabus. Okay. So we are here. Okay, this bit. The derivative of important functions. Okay, we're over there. All of this stuff, down to the optimization and stuff there, that's before the semester break. Okay. Right? Your mid-year break, the between the 2 semesters, is all of that. This leftover stuff is after the break. Okay. So when I tell you, there's a lot to get through, we're at the top there with number 3. We need to get all the way down to the bottom there. Okay. Welcome to university, right? Okay. So I'm not just saying it's a lot, just so that you listen. It's a lot because it's a lot, right? Okay. Derivatives of exponentials. Yeah. But on that syllabus, I will put little markers to show you, what we're going to be covering in the different months. Okay, so you can plan for that. Okay, so an exponential, what is that? So that is some base b with the exponent x. So b, we're not going to be too worried about what that is. So it can be 2 to the x, 3 to the x, something like that. Okay, that's our base to the exponent. Please make sure you know how to sketch these. If the base is a fraction, you need to know how to sketch that. If the base is a whole number, you need to know how to sketch that, right? Because it's reflected about the vertical, if it's a fraction or not. If you don't know what I'm talking about, you better catch up for tomorrow. Yeah, you have to know how to sketch these. So what we want is the derivative of b to the x. Again, we're going to do it the long way from first principles. Then I'm going to have the rule, and then you just use the rule from then on. So this is going to be the limit as h goes to 0, b to the x plus h minus b to the x over h. Right, we've seen this before. You just substitute. And now we're going to simplify. B to the x plus h, we can write as b to the x times b to the h. We can split it up. Limit h goes to 0, b to the x times b to the h minus b to the x all over h. Now, b to the x for the first term and the second term, that has nothing to do with h. we can take it out of the limit. Limit, h goes to 0. We're left with b to the h minus 1 over h. And we're left with b to the x on the outside. Okay. Now, we're not going to prove this, so you don't have to worry too much. But there is a unique number b, right? B is some number. There is a unique number b such that when we do the derivative of that exponential, we get the exponential back. In other words, that limit in the front there will be 1. Okay, there's one number b that does that. You don't need to know where it comes from. You just need to know what it is. Okay, so there is a number. We call it E, Euler's number. It is approximately 2.718. Okay, now everyone get your calculators out. Okay, so on your calculators, please look for the button that has pi. So you've got pi there. You know how to get that number. Around there, there's the E. You'll see the E symbol. Do you see it? You do see it. Okay, so you know how to use pi, right? And then there's the E. That E, put it in your calculator, press equals. Okay, that's this 2.718. You everyone see that? Okay, that number is called Euler's number. Okay, I hope you can get to that number, otherwise you can't do the calculation. So you need to know how to put that exponential in, called Euler's number, such that this limit is 1. Is 1. So what that means is when we do the derivative of an exponential with base e, the result is the exponential with base e, because that limit in front will be 1. So from this, we get that the derivative of the exponential with base e, no other base will this work, only this base e, is then equal to the function back, because that limit in front is 1. Now, from now on, we will only work with base e, no other bases. Okay. Please put a little box around this. Okay. So if I have a function e to the x, exponential, you take the derivative of e to the x, the result is e to the x. Yeah. It is only this function that does this. Okay. So we call this the natural exponential. So natural exponential is when we use the base e for the exponential. Also, we can define the natural logarithm as log, your normal log, but not base 2, not base 3, not base 10, base e. Okay, but instead of writing it like this, we write it as ln of x. Now, I have absolutely no idea, but every single year, students write that as a capital R. Every single lecture from now till the end of the year, I say the word logarithm, 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 and still they write capital R. I have no idea why. I cannot explain it. Every year I've taught this. Please do not write it as capital I. It is a logarithm. L, that is an L, not a capital R. Please, for the love of God, do not write capital I. Please make this the year where I do not see a capital R. Okay. Please, I'm begging you. Do not write capital R. Okay. L for logarithm. Okay. I've got no clue why. Every year. No idea. Anyway, so that is the natural logarithm. And that is the only logarithm we're going to use from now on. So not base 2, not base 3, not base 10, base E. Okay, now again, look at your calculators. Okay, so instead of writing, typing on your calculator log base something, on your calculators you'll see ln. Do you see that? You see the ln? Is it broken? Oh, it looks like an R. I don't know. I keep saying log. I don't know. Every year. Okay, anyway. Push that button for the natural log. And then in the inside put E. So this is log base E of E. And then press equals. You get 1. Okay. Log base 2 of 2 is 1, right? Log base E of E is 1. Okay. But we don't write the base E. So you might forget, you might forget that there's actual base E. But it is in fact log base E of X. We just don't write the base there. Okay. We write ln, but please keep in mind it is always base E. So if you write ln of E, it's 1 because the base is E, secretly hidden there. Okay, so that will be it for today. So 3 things that you need to do for tomorrow. Number 1, go over that binomial stuff. Okay, a plus b to the n. Make sure you know it, top to bottom. Okay, please go through that. We'll be using it tomorrow and later on in that. Okay, second, the homework for the trig functions, the derivative of cos, the derivative of cotan, all of those, go through those. So here, right, these derivative of the trig functions, go through them from first principles. If you don't go through them and you fail that in the class test, that's on you. Okay, I'm telling you, please go through them. All of these from first principles, make sure you know how to do that. And lastly, the tutorial on the derivatives, please start that. So here, tutorial set, sorry, not this one, this one here. Have a look at what we did for limits and continuity. 1, 2, 3, 4 exercises. Does everyone see that? Look at what we have for derivatives. Okay. Do not leave this for last minute. When you get to the test, you are not going to be doing all of this the night before. Start this now. Okay. I'm showing you 1, 2, 3, 4, 5, 6, 7 of these. You are not doing that the night before. I know a lot of you cram before the test. There's no way you are cramming this for the test. Okay. Start now with exercise 2.1. Every week you work through it a bit more at a time. Okay. Do not leave it last minute. You will fail. Okay. You have to go through it a bit at a time. Okay. And then just on the logarithms here, if you forgot your logarithm stuff from high school, please go through that exercise. Okay. When we get to the derivatives of logarithms later on and using logarithms, I expect you to know that exercise 6.6. Okay, we won't be going through it in class. You need to do that in your own time. Okay, so please go through that in your own time. Any questions before we go? All good.